Look around you. The world is alive with motion. But not all motion is created equal. We often see objects moving in straight lines, like a car on a highway. This is linear motion. Yet there's another type of motion, one that's just as fundamental. Rotational motion. Rotational motion is the motion of an object spinning around an axis. Think of a spinning top, a rotating bicycle wheel, or even the Earth spinning on its axis. These are all examples of rotational motion, a dance of objects around a central point. Understanding rotational motion is crucial for comprehending the universe. It helps us explain how planets orbit stars, how galaxies spiral through space, and even how figure skaters execute their dazzling spins. From the smallest particles to the largest celestial bodies, rotational motion is a fundamental principle governing the cosmos. Let's delve deeper into this fascinating phenomenon. Imagine trying to balance a ruler on your fingertip. It's a simple yet fascinating challenge. You instinctively search for its center, the exact point where it rests perfectly without tipping over. This point of balance is known as the center of mass, a fundamental concept in physics.
In physics, the center of mass is the point where an object's entire mass can be considered concentrated. It's a crucial idea for understanding motion. For a simple system of two particles, it's like finding the weighted average of their positions. This helps in predicting how the system will behave. The formula involves their masses, m1 and m2, which are the weights of the particles, and their positions, r1 and r2, which are the locations of the particles.
For a more complex object, like a rigid body, the center of mass is calculated by summing the contributions of all its tiny parts. Each part plays a role. Each part's mass is multiplied by its position, creating a series of products, and these products are summed up and divided by the total mass. This gives us the precise location of the center of mass. The center of mass is crucial for understanding how objects rotate. It determines the stability and motion of rotating bodies. It's the point around which an object will naturally spin, maintaining balance and symmetry. And it simplifies many calculations in rotational motion, making complex problems more manageable and easier to solve. When discussing rotational motion, we need special tools to describe how fast an object spins and how that spin changes over time. These tools are angular velocity and angular acceleration.
Angular velocity, denoted by the Greek letter omega, tells us how fast an object rotates. It measures the rate of change of angular displacement, which is the angle through which an object has rotated.
Angular acceleration, denoted by the Greek letter alpha, measures how quickly the angular velocity changes. Just like linear acceleration tells us how quickly an object speeds up or slows down, angular acceleration describes changes in the rate of spin. These concepts are essential for analyzing the motion of spinning objects. Whether it's a spinning top slowing down or a car wheel accelerating, understanding angular velocity and acceleration provides key insights into their rotational behavior. Imagine trying to open a door. It's a simple action we perform countless times every day, but have you ever stopped to think about the mechanics behind it? You don't push on the hinges, do you? Instead, you naturally push on the handle, which is positioned far from the hinges. You push on the handle as far from the hinges as possible. This is because pushing at a point far from the hinges makes it easier to open the door. That's because you instinctively understand torque, even if you don't realize it.
Torque, denoted by the Greek letter tau, is the rotational equivalent of force. It's a fundamental concept in physics that explains how rotational motion is generated. It's what causes objects to start spinning, stop spinning, or change their rate of spin. Without torque, we wouldn't be able to perform many everyday tasks. Just like a force can cause an object to accelerate linearly, torque causes angular acceleration. This means it can change the speed at which something rotates. The magnitude of torque depends on three things: the force applied, the distance from the axis of rotation to the point where the force is applied, called the lever arm, and the angle between the force and the lever arm. These factors work together to determine how much torque is produced.
A longer lever arm and a larger force both result in a greater torque. This is why tools like levers and wrenches are designed the way they are. Think of using a wrench to tighten a bolt. The longer the wrench, the less force you need to apply to achieve the same tightening effect. A longer wrench requires less force to achieve the same tightening effect. This is a practical application of torque in everyday life. Torque is everywhere in our daily lives, from opening doors and turning steering wheels to pedaling bicycles and playing on seesaws. It's an essential part of how we interact with the world. It's the invisible hand that sets the world spinning, whether it's the giant blades of a wind turbine or the small gears in a watch. Torque is at work making things move and function. Section 5. Momentum's pirouette. Angular momentum. Angular momentum is a fascinating concept that plays a crucial role in the world of physics and beyond. Just like objects moving in straight lines have linear momentum, rotating objects possess angular momentum. This property is essential in understanding how objects behave when they spin.
This quantity describes the tendency of an object to keep spinning. Whether it's a Ferris wheel at a fair or a merry-go-round in a playground, angular momentum keeps them in motion.
Angular momentum, denoted by the letter L, depends on both the object's moment of inertia, which we'll discuss in the next section, and its angular velocity. These two factors together determine how much angular momentum an object has.
One of the most fundamental laws in physics is the conservation of angular momentum. This principle is observed in various systems, from simple toys to complex astronomical phenomena. This law states that in a closed system, where no external torques act, the total angular momentum remains constant. This means that the angular momentum of a system doesn't change unless acted upon by an external force.
This principle explains why a figure skater spins faster when they pull their arms in. By pulling their arms closer to their body, they reduce their moment of inertia. By reducing their moment of inertia, they increase their angular velocity to conserve angular momentum. This is a perfect demonstration of the conservation of angular momentum in action.
Similarly, the Earth's rotation keeps it spinning steadily in space. This steady rotation is a result of the conservation of angular momentum on a planetary scale.
Understanding angular momentum and its conservation helps us explain a wide range of phenomena, from the motion of celestial bodies to the stability of rotating machinery. This knowledge is crucial in fields like astronomy, engineering, and even sports. It's a cornerstone of our understanding of the universe's intricate dance. The concept of angular momentum allows us to appreciate the beauty and complexity of the world around us, from the smallest spinning top to the vast movements of galaxies. Now let's dive into the concept of moment of inertia. This is a measure of an object's resistance to changes in its rotation.
Essentially, it's how mass is distributed relative to the axis of rotation. The further the mass is from the axis, the higher the moment of inertia.
The formula for moment of inertia varies depending on the shape and mass distribution of the object. For instance, a solid disk and a hollow ring of the same mass and radius have different moments of inertia.
This concept is crucial in understanding how objects rotate and how we can control their rotational motion. It's applied in designing everything from wheels to spacecraft.
By mastering the moment of inertia, engineers and scientists can predict and manipulate the rotational behavior of objects, leading to advancements in technology and a deeper understanding of the physical world. Inertia calculations can often be quite complex, but there are ways to simplify them.
That's right. By using the parallel axis theorem and the perpendicular axis theorem, we can make these calculations more manageable.
Understanding equilibrium in rotating systems is crucial for many applications.
Absolutely. When a system is in rotational equilibrium, the sum of all torques acting on it is zero. This principle is essential in designing stable structures and machinery.
Rotational motion isn't just a theoretical concept, it has numerous practical applications.
Indeed. From the spinning wheels of a car to the turbines in a power plant, rotational motion is everywhere. Even in ancient history, the invention of the wheel revolutionized transportation and machinery.
So there you have it. Rotational motion is a fundamental concept that not only explains the behavior of spinning objects, but also has far-reaching applications in our daily lives. Understanding these principles can lead to innovations that drive progress in various fields. Thank you for joining us on this journey through the fascinating world of rotational motion.